When we discuss the integral test, we use the idea of comparing our series to a similar function and looking at the series integral as a way of approximating the sum of the terms in the series. And we said, all right, well, if the integral is an over approximation for what the sum of our series is looking like or behaving, then we know that this series must also do the same thing that the integral does. If it converges, since it's an over approximation, then our series also has to converge. If it diverges, then our series is going to behave similarly. Now, again, look back to our integral test video if you need some help kind of reviewing that. But we're going to apply a very similar line of reasoning here with our comparison tests. And these are the final tests that we are going to look at in this course. And the direct comparison test to start says the following. If you have two series, one which we'll describe as A sub n and the other as B sub n, and if A sub n is less than or equal to B sub n, meaning we've got a quote unquote smaller series and a larger series, so let me just write that. We've got a quote unquote smaller series here, smaller, and you're gonna see me kind of describe this as the quote unquote larger series here. If they both contain positive terms, then we can state that if A sub n, our smaller series, diverges, then by comparison, B sub n, our larger series, must also diverge. So let's just kind of think about this for a second. And while this graph that I'm about to draw doesn't show exactly what's happening with series, I think kind of thinking about them as functions gives us a good sense of why this intuition makes sense. If A sub n is our quote unquote smaller series, let's just kind of draw that. Let's draw a series that diverges. So for example, let's say the terms are slowly getting larger. That's something like that. We'll just say that this is A sub n. And before I draw B sub n, let's just think about this for a second. If B sub n is the larger series, and you know that A sub n, every term in A sub n is less than or equal to every term in B sub n, if your smaller series is diverging, then you have no choice. B sub n has no choice but to also diverge as well. B sub n can't suddenly converge because that would mean that those terms are getting smaller when that's not happening with A sub n. Now, what about if we were to flip this around? What if B sub n, let's just kind of let me erase this. What if B sub n, which is again our larger series, converges? Well, what does that then tell you about A sub n? Well, if your larger series is converging now, then A sub n also must do the same. A sub n must also converge. Let's take a look at this now with two actual series. Let's say, for example, we had one series was n is equal to 1. Let's say this was our given series. We have 1 over 2 to the n plus 1, something like this, okay? Now, let's take a look at another series. Let's compare that to the following n is equal to 1, infinity, and let's look at 1 over 2 to the n, a pretty familiar series at this point. So first off, stop and ask yourself, which is the quote-unquote larger series? Well, hopefully you were able to identify that this one has a smaller denominator, therefore each term is an overall larger ratio. So this given series that we had was a smaller series. And what we have here is I'm going to kind of describe this as my helper series here. This is what I'm comparing it to. And my larger series here, so I can actually just change this now and say that this is now, this is going to be the following. It is greater than this series, it's a larger series. Well, what do we know about our larger series? This one is going to converge. How do we know it converges? Well, if we think about this as a geometric series, we know that this absolute value of our ratio r is equal to 1/2, which is less than 1. So this series converges by GST. So again, if your larger series now is converging by GST, that means your smaller series also has to now be converging. This now also has to converge. Also, let me write that, also converges by the direct comparison test. And I'll do another problem in a second where I'm a little bit more clear with what work is required to receive full credit on problems like these. But hopefully this just gives you a sense that, yeah, if you really just intuitively think about it, if your larger series is converging to a finite sum, then your smaller series that has smaller terms has to also converge. It can't suddenly diverge. So a couple of notes to help us think through this as we approach some of these problems. So the first thing is, When determining a helper series, you want to first choose a helper series that you can easily determine its convergence or whether or not it diverges. It doesn't make sense to come up with a really complicated helper series where you have to spend a whole lot of time trying to figure out if that series converges or not. Typically, that means we end up using a p-series test or p-series or geometric series, as those are pretty quick and easy. And this part is actually pretty important when it comes to uh, the direct comparison test. We want to say the following. If we have, if we think that our series converges, if we think that our series should converge, we want to choose a larger helper series. So pause and think about that. If you think that your series converges, you want to make sure that your larger series that you're comparing it to converges. Similarly, if you think that your series is going to, let me just do a different color. If you think your series is going to diverge, right? If you think that your series is going to diverge, you then want to come up with a smaller helper series. Because again, if all the terms in your helper series are smaller, but that series diverges, your larger series that's quote unquote on top of that has to also do the same. All right, so let's try a couple of quick problems with this. Let's try example number 1. Well, looking at this, the first thing we want to ask ourselves is, all right, do we think that this series is going to converge or diverge? Well, my sense should be that this series converges. As our denominator gets larger and larger, it would make sense that your subsequent terms would approach 0. So I'm going to compare this to another series that I know for sure converges, okay? But more importantly, I want to choose a series that I know that converges, but also is going to be quote unquote larger than this one. Well, how would that be larger? Really pay attention to the degree here. If you know that your degree of your denominator is a quadratic, then a quick and easy series to compare it to would be n squared, 1 over n squared. I know that this series is larger than the series that we were given. How do I know that? Larger denominator means these terms are going to get smaller because my denominator is larger. Also, I know that this series, and let's write this, we know that this series here does what? It converges by the p-series test, right? Because our p-value is equal to 2, which is greater than 1. So that series converges by the p-series test. So if you know that that series, our larger series, is converging by the p-series test, what does this tell me? This means then we need to write this. N is equal to 3 infinity 1 over n squared plus 3n plus 2. Let me just clear that out of the way. We know that this series then also converges by the direct comparison test. Now, I want to do a couple quick things here as an exercise just to make sure you understand the importance of why each thing that's listed here is going to be essential for you to, justify your answer completely and thereby get full credit. So one thing that I often see students do is I'll see them not write this here. They'll come up with a helper series, right? And they'll show why that helper series is either convergent or divergent. But you can see that not having that inequality there is pretty crucial because if you were to come up with a smaller series that converges, well, that doesn't tell you necessarily that your larger series also does the same. So that's going to be important. As is expected, anytime you use a convergence test, you need to show its full justification. So for example, if you were missing all of this, that would not be enough to justify by the p-series test. You can't just state the name of the test. You have to give the justification. Similarly, I oftentimes see students do this with the p-series test. Well, they'll say, oh, my p-value is equal to 2. Well, what about the fact that that is 2 tells you that your series converges? So you want to show that the p-value is greater than 1. And then finally, one thing that I often also see students do is they'll say something like this. They'll say that series converges by DCT, something like this, for example. Well, I'll ask, well, which series converges by DCT? I know you wrote this about the helper series, but you've got to make it explicitly clear. So I know it's a bit of a nuisance to have to rewrite the whole series sometimes, but you know what else is also a nuisance? Losing points on a problem that you know for sure that you thought you answered correctly. Okay? Let's do one more for the direct comparison test. Let's try a problem like this, and there's a little bit of a typo here, and hopefully you can spot it. And you should say that the lower index should be 3, or I should have written that. Because the direct comparison test only works with every term being positive. And had I started at 1, what's the natural log of 1? Well, that's 0. So this series would not contain all positive terms. So now that I fixed that, let's now again look at the series. We know that our numerator is unbounded. It's going to continue to grow without bound. And the same can be said about the denominator. It's going to approach infinity. So my intuition is that this series might diverge, but that's not enough to fully definitively state that it diverges. So again, what would be a series that I would want to compare this to? So let me start setting this up. What would be a series that I would want to compare it to that I know for sure is going to be a series that diverges, and as a result, I want it to be my smaller series. So what would be a quote unquote smaller series that you know diverges? Well, hopefully you didn't have to think too long because we just talked about it recently in this course. It'd be 1 over n. And this is a great series to compare it to because our denominators are the same, but look at our numerators. 1, our smaller series, is constant, whereas our quote unquote larger series is going to continue to grow without bounds. So this is a great series to compare it to. So what do we know about this series here? We know that this series here diverges by either you can say the P series test, in which case you would have to write that we know that P is equal to 1, right? Or honestly, you could also just say you can just divergent because it's a harmonic series, right? It's accepted that the harmonic series at this point is a divergent series. So you don't have to necessarily use a series test for that. Again, we know that this is a smaller series. So our series that we're trying to determine its convergence for is the quote unquote larger series. So now that we have that, and you know your smaller series diverges, we can then say, therefore, our, oops, not 1, we just established this, our series here, natural log of n over n, also, oops, there we go, also diverges by the direct comparison test. Okay, well, hopefully that makes sense and you have a good sense of how the direct comparison test works and what would be required when we are showing a series convergence or divergence using this test.